in this presentation, I'll make it short so it fits into 15 minutes. I'll introduce some basic concepts and later snapshots of the results which we have so far, because the project has been going now for some time. Okay, so there'll be introduction, then because the project is application of intelligent systems, it is machine learning and some basic concepts. We'll introduce an experimental setup because the work which we are doing involves a lot of experiments to collect data. And I'll also show what technique of AI technique we do. We use artificial neural networks, and we'll go arriving to some fundamental conclusions. Okay, this is working now, thank you. So why the project we are doing? It is a well-known fact that a large proportion of faults or damage, which we use rather than faults, are due to failures or different parts in doors. And we have a power-operated door system that's quite complex, and it involves landing and car doors and the operator. So that's quite complex system. And that's the schematic representation, which we know probably everyone. It is from our textbook. So it's power operator, which involves drive, control, and anything else which is involved in it. Okay. So when we collect data from the system like this, we are looking at signs of wear and tear. And when we started this project, we looked into how to classify our terminology, because that's a very important stage. So we decided to use damage rather than fault, because the definition of damage is when the system does not operate as it should, but it still can operate. The fault we define in this project is when the system does not work at all, because that is basically broken. So that's what we say. So when we have this in mind, we also looked at what would be the proper hierarchy of approach. So the approach will be in first detection. So what happens in terms of qualitative behavior, well, lost quality of service, for example. And later, what is a localization of the damage? So what is broken, where it is broken, and how we can see it. And also how to classify it. So what type of damage would it be? And then we can do assessment. And once we have assessment, we can predict. So the prediction in the future, how we could mitigate the possible damage so the system operates still okay, okay? And that's the part which we are still working on. So in terms of the methodology which we are using, we collect data. So the data which we are collected as later are introduced into machine learning models. And the machine learning is obviously linked to artificial intelligence. So what is artificial intelligence? It's the computer system, it tries to mimic human brain, okay? What is machine learning? Okay, there's many definitions of those, but it's quite broader techniques which define algorithms which enable computer to learn tasks. That's why it's learning here. There are some other related concepts I later mentioned after that. And then within machine learning, there are many techniques. One of them is called pattern recognition. So in pattern recognition, and we apply this in machine learning, what we are looking is to process, to classify input data into objects or classes. So that's here another important concept, class of damage. So we are using class of damage to identify what we are doing. Pattern recognition algorithm assigns then a label to a class. And once we got the label, then we have we attach to this label a sample of measurement. So typically it would be, in our case, vibration. It could be also acoustics or many other things. I think we got a couple of presentations earlier on that mentioned this. So as soon as we have a class label, okay, we can encode damage and possibly locations, because that's linked together. All right, that's a simple here diagram. It shows this progress, machine learning, pattern recognition, and then there are two types again. Two types. One of the types is called unsupervised learning. That means it does not involve training. the system propels itself, finds everything and tells us. That's difficult, not always feasible. The other class is called supervised learning. Supervised learning involves training. So what we take a set of measurement data, which are arranged into structural vectors, for example, or matrices, which mathematically is being done that way, which uniquely are associated with each class of damage. So we train the system to recognize, here's a class 1, here class 2, class 3, class 4, okay? So the challenge is that needs to be done for any conceivable damage which could possibly occur in the system. And that might be tens or 20s or hundreds. In most cases, we just limit ourselves to some fundamental damage. Okay, then we use algorithms. The algorithms which are implemented to do that, there are many. But however, the most popular is neural networks, artificial neural networks. So what it is, probably many of you have seen this type of graph on the screen, somewhere in the books. Neural networks mimic human brain. So main part of the human brain is called neuron. So neuron is here on the left-hand side, neuron 1, neuron 2, and they are connected, they have neuron 3, and so on. They talk to each other. They have got multiple inputs and multiple outputs. Here's a mathematical model. So when we do pattern recognition, we use this kind of models. So what it does, we've got input, and then we've got a set of parameters, which I refer to as bias and weight, which are used to process the input, and they are being fed into what we call activation function, which probably more or less this involves the one cell in the system. And what we get, you get an output, and this output is just going to another layer of neural networks. Eventually, we have something like this. And this is related to classifying neural networks into shallow or deep, and then from machine learning to deep learning. Okay, so that's the fundamental. That's a sigmoid function here, which involves exponential function, most common, but there are many others. Okay, so no mathematics anymore. Now, that's the picture which shows our experimental setup. In our lab, we have a setup which accommodates different types of doors. For example, here on the left, it is single panel side opening door, single speed. This door is center opening, single speed, 2 panels. And here is another set of doors, 2 panel, double speed, 2 speed, side opening. We have more to come. So that's what we do. What do we take? We take sensors, we place in strategic points of the structure, and we record vibration. And when we take vibration, we can do further work. Okay, so what do we do? Okay, this picture shows here the fundamental measurements which we do. Okay, the door motion is monitored in specific location. We use accelerometers. So we record acceleration. So for example, here, that's the acceleration which is recorded in one of the doors. All right, I mentioned that you can see this -1 to 1 is normalized. It's not, we apply normalized values, not the unit value, but normalized values. Once we have those, okay, collected via DAQ, data acquisition system, we go further because the time data domain is not always very good to use in artificial intelligence. Normally we use frequency domains. So what we use spectrograms, which shows frequency spectrum against time, okay, and magnitude. All right, we tried to do this, and also the most successful methodology is to use what is referred to as cepstrum or cepstrograms. That's a Fourier transform of the logarithmic spectrum. And that's very similar to spectrum, but different. It turns out that picks up better the damage, okay? So here's an example of damage classes. Okay, notice that, excuse me, class 1 is no damage. So there's a reference level. What system is what very often in machine health monitoring is referred to as healthy. So no damage, everything operates well. So we take the measurement and record it. Later on, we see the damages. So this graph shows 8 possible classes now, 1, 2, 3, 4, 5, 6, 7, 8, including no damage. And then we got damaged car door roller, damaged landing door roller, and so on. Up to, we have also one which is quite often used as a misalignment in the system. So it's not real damage, but there's interlock misalignment, so misadjustment. It is also damage because it leads eventually to the problems with the system. And how they are represented in the algorithm is a sequence of ones and zeros. So we have 8 classes. Vector here has got 8 values. 1 indicates first class, 2 second, 1 second class, rest is zeros. And that is the fundamental to the training of the network. Basically, we take the network and we input data, and those data are being trained to recognize those numbers. So everything is about numbers. Okay, so that's an example here. There's a neural network. In the first approach, we use something very simple. Still, we are stuck with this because it turns out it's not that simple. It has got its complexities. So what it shows here, shows what is referred to as a shallow neural network. Shallow means it has got 2 layers maximum. It can have 1 layer, but normally it's a 2 layer. But it can have more than 1 neurons. It can have tens, hundreds, thousands. So, okay, so then when we have this, luckily, we don't need to do everything from scratch because there are neural networks already in libraries, and we use MATLAB libraries. There's a tool which is called Neural Pattern Recognition Tool, NPR tool, and that works very well. You can code it, and we get some results. So that's an example. For example, for training now, we have an input. We input data set, goes through those, and go to output. And when it is trained, we get network. With all the neurons now are trained, and those, remember, there are bias coefficients, weight coefficients now adjusted. So it's all about mathematics here. Okay, there's an example what can be achieved. After neural network is trained, we take our measurements as input data, and then see what comes out. And the method to judge is to produce so-called confusion matrix. So that's an example of confusion matrix. Okay, what it is here, again, very briefly, it could spend a long time to explain, but the rows correspond to the predicted output class. So for example, class 1, 2, remember class 1 was no damage, 2 was roller at the car side, and so on, and so on. And what is here on the columns is the true or target class. So those are those 0, 1, 1, or 0, 1, 0, 0, and so on. And you can see here that they are mapped together. And what we get here on the diagonal, we see the numbers which indicate accuracy. So accuracy is here. Okay, let's take number 3. So that's number 3. It was landing door damage. Okay, landing door roller damage. It has been misclassified. 5 samples of the measurement were shown as 8. And what was 8? Interlock. Okay, but if you go here, 3 and 3, we've got 528 samples are classified correctly. So eventually this adds up, and what we get here in this experiment, you get 97.6% accuracy. That's what is good. Anything which is above 80% is considered good, okay? So that indicates the concept. So where we are now is that we obtain very good results, in our view, which you can use and expand. So we have excellent accuracy overall, because it's good over 90%. Now, the work completed so far forms the basis for inclusion more damage, because I said we've got 8, 9, you can get more. doors, but we can also add anything else, car, the whole structure. And then we've got a lot of data here. So that's future work which we are doing. And also what we want to do is to improve still, okay, when the system grows, the accuracy will fall. We need to apply better neural networks. So we're going into deep learning. So that is something which is called convolutional neural networks, which are pre-trained, and we apply what is called transfer learning to get this work in our case. Again, good news again, that those networks are available. We don't need to do them from scratch, but we as engineers, we need to know what we are doing. Okay, so once we've got all this done, the next stage will be to, okay, come up with some predictions. What can we do to have predictive maintenance in place, which takes all this into account? So let's complete this short presentation. I would like to acknowledge support from our partners, TK Elevator. So thank you. And we've got there on our stand simple demonstration tool, which would show more or less what we are doing on a simple example. And you see there accuracy is 100%. Thank you.